Hi, my name is Isabelle and I'm a sophomore at the Harker School. My research project is AI-powered solar flare forecasting, enhancing the data efficiency of LOS magnetogram images with the EfficientNet algorithm. Let's begin with discussing solar flares. Solar flares are explosions of energy and radiation, mostly X-ray and gamma ray radiation, that occur due to the bursting of strong plasma-filled magnetic loops on the sun. Solar flares are classified into A-class to X-class based on the peak strength of energy released, with C1 and larger flares being able to cause significant geomagnetic disturbances and X-class flares able to incite intense solar storms. Before diving straight into how flare forecasting works, it is important to understand why solar flares pose such a large threat. The radiation emitted by these flares often ionize the ionosphere, leading to disrupted satellite systems, communication blackouts, and serious risks to nearby astronauts and high-altitude flights. Between 1996 and 2010, solar flares were responsible for nearly 20% of all satellite failures, making them a critical threat to modern infrastructure. Additionally, it is reported that a single X-class solar storm can cause up to $17 billion in global economic losses. For instance, the graph on the bottom shows the X-ray radiance detected during a X9.3 flare that caused a radio blackout amidst a hurricane, which brought about devastating consequences for first responders and victims. Because of these potential risks, researchers have developed several flare forecasting techniques, one of which are machine learning-based models. Typically, machine learning algorithms predict whether flares will occur within a given time period and rely on either solar image datasets or physical feature datasets, which are values extracted from solar images. However, the process behind physical feature value extraction and its maintenance make algorithms very computationally inefficient, as they often have to be manually selected or often adjusted. On the other hand, models based on solar images itself require hundreds of thousands of these input images just to capture complex spatial patterns and achieve acceptable model performance. As a result, the development of forecasting systems that are not only predictively powerful, but also have overall efficiency have become increasingly vital for the field of space weather. Now here's where EfficientNet comes in. Developed as an optimized version of convolutional neural networks, EfficientNet leverages a compound scaling technique to achieve higher accuracy with fewer model parameters and enhanced training speeds. In my research specifically, I experimented with both the original and more complex EfficientNet V7 models and two EfficientNet V2 variants, EfficientNet V2B2 and EfficientNet V2B3. These EfficientNet V2 variants utilize fused NB convolutional layers and a progressive learning strategy for improved training efficiency. My research aimed to develop an EfficientNet-based flare forecasting model that was able to predict whether a C1 or larger flare occurred in the next 24 hours from a singular solar image. In terms of research objectives, I aimed to evaluate the EfficientNet architecture's capability to generate novel, reliable forecasting systems, identify optimal hyperparameter configurations for resource-constrained flare classification tasks, and investigate how varying EfficientNet model complexities affected overall predictive abilities. My models relied on full-resolution line-of-sight magnetograms collected from NASA's HMI instrument. These images map the strength and polarity of the sun's photospheric magnetic field, with white and black representing positive and negative polarity, respectively. To minimize projection distortion caused by the curvature of the sun, only active regions within 60 degrees of the solar central meridian were included in my dataset. Binary class labels were then generated with GOES X-ray flux catalogs, for which positive class elements consisted of magnetograms that produced flares within 24 hours of image capture, while the negative class consisted of the remaining non-flaring magnetograms. In total, I utilized around 60,000 images across 447 solar active regions, which equated to around 100 gigabytes of data. The training, validation, and testing datasets were structured into unique active region groupings, ensuring that each model's testing accuracy wasn't inflated just because it was already exposed to magnetograms from the same active region previously. Furthermore, due to the rarity of flares, positive class elements only accounted for less than 20% of the total data. Because of this, to prevent model biases and minimize data skewness, I rebalanced the training and validation datasets while keeping the testing datasets in balance to reflect real-world class distributions. On top of that, I also created image data generators for the training and validation datasets, which fed input images into the model in batches. This allowed for a more efficient memory usage by loading only a portion of the dataset into memory at a time, rather than the full set of 60,000 images. It also enabled data augmentation during training. For example, the random rotation, random flip, and shuffling of input data as shown in the examples below. All model training was conducted in a TPU environment and compiled using the Atom Optimizer with a categorical cross-entropy loss function. To adapt IfficiNet for binary flare prediction, I modified the classification head by replacing the original output layers with a global average pooling layer, followed by a dropout layer for regularization and a final dense layer for classification. To prevent overfitting, early stopping was implemented. Training was halted when models achieved over 95% accuracy on the training set, while dropping below 70% on the validation set, which indicated poor generalization. Additionally, I varied a range of training configurations, such as the data resolution of input images, the batch size of the image data generators, the learning rate, class weights, and the IfficiNet model versions. Throughout both training and testing, model performance was evaluated using multiple metrics, including classification accuracy, sensitivity, specificity, true skill statistic, and F1 score. Here is a table detailing results for different model configuration combinations on unseen testing data. Most of my models achieved classification accuracies of around 82%, with the best performing model reaching an 85% classification accuracy. In particular, this best performing model was able to correctly identify 15,000 elements of the negative non-flaring class and 4,600 elements of the positive flaring class. Furthermore, this M2 model achieved a true skill statistic of 0.64, which falls within a strong and operationally meaningful range for solar flare forecasting. The model also reached a true positive rate of 78% and a true negative rate of 86%, with an F1 score of 0.85, indicating relatively balanced and reliable performances across both classes. To highlight the efficiency of my model, I compared the total data volume used in this study to several recent approaches. As shown on the right, my model utilized the least amount of training data, less than an eighth of the data used in certain studies. Each training epoch, processing about 60,000 images, took approximately 3.7 hours. That translates to a training time of roughly 200 milliseconds per image and an inference time, the average duration the model spends on predicting new, unseen data, of just 70 milliseconds per image. This makes IfficiNet significantly faster than traditional models, which typically require 100 to 300 milliseconds per image for inference. Here I compared the best performance of my M2 model against other model architectures produced by the studies in the previous slide. As shown in the chart, my M2 model achieved TPRs comparable to those reported by other state-of-the-art models and even surpassed the TPRs of ResNet 18, SqueezeNet, and VGG16 models. For instance, compared to SqueezeNet, my model demonstrated a 5% improvement in recall while being trained on almost 10,000 fewer magnetogram samples. Additionally, it is important to note that a Botron 2023 study reported a recall of just 69.52% using a VGG model on the exact same LOS magnetogram dataset, reinforcing the strength of IfficiNet over traditional CNN versions. These results confirm that IfficiNet not only competes with, but advances beyond several state-of-the-art CNNs, offering higher performance with fewer resources, making it a highly effective choice for solar flare forecasting. Next, I looked at how IfficiNet B7 and IfficiNet V2 models differed in both accuracy and learning dynamics. All IfficiNet models showed strong learning on the training set, but IfficiNet V2 models reached a much lower training loss within 5 epochs, around 0.1, compared to a loss of 0.5 for IfficiNet B7 models. Additionally, B7 models tended to favor higher true positive rates, while B2 models leaned towards higher true negative rates, as shown in the graphs below of the validation accuracy over 5 epochs. In terms of impact and real-world application, this study demonstrates IfficiNet's overall effectiveness in complex, large-scale image classification tasks, specifically in space weather forecasting. With its ability to classify over 50,000 LOS magnetograms per hour, MyFishNet model enables rapid identification of potential solar threats, providing up to 24 hours of advance warning for specialists to mitigate damages on satellites, communication systems, and human technology in general. In addition to its predictive strength, my model also reduces training time by up to 80% and energy consumption by 85%, representing an estimated savings of over $2,000 per training cycle of 10 epochs. Taken together, these results position this EfficientNet-based system as a practical, scalable, and globally impactful solution for operational space weather monitoring and early warning systems. In conclusion, the best performing EfficientNet model developed in this study achieved an overall accuracy of around 85%, surpassing the performance of previous models despite relying on a substantially smaller training dataset and therefore achieving the set engineering goals. In addition, the results reveal a clear trade-off between model complexity and predictive behavior. EfficientNet V2 models, though less complex and faster to converge, tended to favor higher true negative rates, minimizing false positives. In contrast, the deeper and more complex EfficientNet B7 models consistently achieved higher true positive rates, making them better at capturing actual flaring events. In terms of optimal training configurations, more complex EfficientNet models were more sensitive to imbalanced class weights, while smaller variants showed greater stability across different weight settings. Overall, all EfficientNet models showed better performance metrics with larger batch sizes and higher learning rates. Finally, future research directions include 1. Expanding the dataset using magnetograms from additional observatories, 2. Developing hybrid EfficientNet ensembles, 3. Addressing the imbalance between true positive and true negative rates, and 4. Implementing multi-class classification to capture different flare intensities. Here are my references, and thank you so much for listening. Please contact my email if you have any questions.